As you should recall from our last lecture, parametric tests have multiple assumptions, but a common assumption is the assumption of normal distribution. However, the reality of nursing is that we are often conducting research or projects where our sample distribution is going to be non-normal. This is usually related to having to rely on small samples or convenient samples. If we were to use parametric tests of statistical analysis in these situations, both the internal and external validity of our results would be violated. Thankfully, non-parametric tests provide us with a solid option for being able to statistically analyze our data when the assumption of normality is violated. Following this lecture, students should be able to explain when to use non-parametric tests of statistical analysis to compare groups, discuss ranking and effect size for non-parametric tests to compare groups, distinguish between when to use each of the 4 non-parametric tests discussed in this lecture, list the assumption for each non-parametric test discussed, and describe what results to report for each non-parametric test discussed. Non-parametric tests serve the same purpose as their parametric counterparts by evaluating if one variable had an effect on another variable. Like parametric tests, each non-parametric test has specific assumptions that must be met for the test to produce valid results. However, normal distribution is not an assumption of non-parametric tests. While parametric tests analyze data by comparing group means, which relies heavily on a normal distribution to get valid results, non-parametric tests analyze the data by comparing the ranks of the data, not the actual raw data. For this reason, while non-parametric tests are less powerful than parametric tests when data are normally distributed, they become more powerful in finding an effect when the data are not normally distributed. On the upcoming slides, we will talk about the non-parametric tests that serve as the counterparts for the independent and dependent t-tests that we previously discussed. I will also introduce you to 2 non-parametric tests that will allow you to compare several groups. We did not discuss parametric counterparts for these tests because the parametric counterparts are rarely used in clinical practice as the assumptions are challenging to meet. However, many clinical practice problems will lend themselves to comparing multiple groups, and these non-parametric tests offer the best methods for accurately analyzing such data. Before we proceed in discussing specific tests, I wanted to pause and provide you with a word on ranking. I've already stated that parametric tests analyze data using the means, which we talked about when we learned about descriptive statistics. Non-parametric tests analyze data using the ranking of the values. Specifically, they use a formula called the sum of rank values. How do we rank the data? To rank the data, you simply put all of the data values for the groups together from smallest to largest, as if you were going to calculate a range. You then assign a rank to every data value. The smallest value gets ranked as 1, the second value gets ranked as 2, etc. If there are 2 or more values that are the same value, you average their ranking order, and all numbers with the same value get the same rank. You then add up not the values themselves, but the ranks for the values in each group. If the groups are not the same size, when you perform your testing, you would use the sum of the values for the smaller group. If the groups are the same size, then you would perform your analysis using the sum of the values, that is the smaller number. To help you understand this, we will walk through an example on the next slide. This slide on the far left-hand side contains a small data set that I made up with 2 groups of RNs from Unit A and Unit B. I have 5 RNs on Unit A and 4 RNs on Unit B, and I have recorded the ages for each of these RNs. If we wanted to do an analysis using non-parametric tests, we would be comparing the ranks. And so to help you understand the sum of rank values, we're going to walk through an example with this data set. The first step is to put all of your values for RN ages in order from smallest to largest. This is all of the values from both groups. So you can see on the table on the right-hand side, I have the raw values listed from smallest to largest. The next thing you will do is you will rank the values. The smallest value is 20. It's ranked 1. It's in the first place. The second smallest value is 22. It's ranked 2. It's in the second place. You will notice there are two values of 31. These would be in the fourth and fifth places. However, there's no real way of saying which 31 is bigger and which 31 is smaller. Therefore, since it is ranks number 4 and 5 that are the same, we take the average of 4 and 5, which is 4 plus 5 divided by 2 equals 4.5. And so each of those numbers gets the ranked value of 4.5. As we move forward, the next number, 33, is not the fifth place, but rather the sixth place in line. So we go back to starting with whole numbers at 6. We would continue this process, which I did for all 9 values. The next thing that you need to do is you need to sum the ranks for each group. You will notice that when I wrote out the raw values, I had group A in red and group B in blue. This made it very simple for me to go back and look to sum the values. So the red ones are group A. So we have 22, that's rank 2, 28, that's rank 3, 31 is rank 4.5, 34 is rank 7, and 37 is rank 8. I am not adding the raw values together. I am adding their ranks together, as you can see on the slide. I do the same thing with the ranks for group B. Now, my groups are different sizes. Group B has fewer RNs in the group than group A. Therefore, the ranking, the sum of ranks that I will use for statistical analysis is group B because there are less people in the group. If there was the same number of nurses in both groups, I would use whichever sum was smaller to be the sum of ranks that I would use for analysis. Again, I want to reiterate, you are not going to be asked to calculate this value. Yes, I had a data set of 9. That was not very challenging for me to rank these and then do the calculation by hand. However, your software will be able to do this calculation for you. I show you the calculation to help you better understand what is meant by ranking the data in non-parametric testing and to help you understand how that is different than the mean of the data which we use in parametric testing. Before we head into specific non-parametric tests of analysis for comparing groups, I wanted to briefly discuss the concept of effect size for non-parametric tests. Back in our lecture on hypothesis testing, I discussed Cohen's D and Pearson's R as two measures of effect size. Cohen's D is the measure used when you are comparing means, and Pearson's R is a measure of comparing correlational relationships. However, both of these measures are generally used with parametric data, not with non-parametric data that do not meet the assumption of normal distribution. However, effect size is important to calculate with non-parametric data. Therefore, since our data is non-normally distributed, we will be using a standardized effect size statistic, which is denoted as a lowercase r. I have the formula for the standardized effect size statistic on the slide. It is z divided by the square root of n, where z is the standardized test statistic and n is the number of observations. What I want to bring attention to is that both Pearson's R and the standardized effect size statistic are denoted as a lowercase r when reporting results. If it is a correlational relationship, a Pearson's R is what the R is. If it is a non-parametric test comparing groups, the R is the standardized effect size statistic. This is something that statisticians infer, but something that can be a little bit confusing at first for those of us who may not use these letters on a regular basis for statistics. Now, you will not be expected to calculate the R effect size by hand. This is something that most software will automatically output when you run the non-parametric test of analysis. Not only will it give you your test statistic and your p-value, it will also give you your R value for effect size. What you need to be aware of is how do you analyze that R value? And I have written that here. A small effect is an R less than 0.3. A moderate effect is an R between 0.3 and 0.5. And a large effect is any R that is greater than 0.5. And remember, again, the effect size is telling us about the clinical significance of our findings. So now that we have this foundation, we are ready to discuss specific tests of non-parametric analysis for comparing groups. The Wilcoxon rank sum test, or Mann Whitney test, is the non-parametric counterpart to the independent sample t-test and should be run when you are comparing two independent groups, but the assumption of normality for the independent sample t-test has been violated. The Wilcoxon rank sum test and Mann Whitney test are essentially the same test. No matter which one of these two tests you run, you are going to get the exact same test statistic output. A little bit of history. Mann and Whitney were developing a non-parametric counterpart to the independent t-test at the same time that Wilcoxon was. These two groups came up with two different formulas. However, both formulas provide the same test statistic. The mathematics to explain how this works are beyond the scope of this course, but trust me, you get the same test statistic, regardless of which process you follow. Therefore, these two tests can be used interchangeably. One is neither better nor worse than the other. And so you may see either one or the other mentioned as the test that was run in the literature. You just need to understand, regardless of which one you say, it is the same test statistic that is obtained, and it is the counterpart to the independent t-test. While non-parametric tests do not have an assumption of normality, they still have other assumptions that need to be met. And the assumptions for this test include three things. First, your sample must be random. Second, the two groups that you are comparing must be independent of each other, meaning that each member is in exactly one and only one group, and the level of measurement is at least ordinal, which makes sense because we need ordinal data to be able to rank our data. So for these tests, you would, just like parametric tests, need a null and alternate hypothesis. The null hypothesis would most likely be similar to a statement such as the distribution functions are identical for the two groups. In other words, the distribution of the ranks is identical. The alternate hypothesis then would say that the distribution functions are not identical for the two groups. As with all tests of statistical analysis, you would use software such as Microsoft Excel or IBM SPSS to compute the test statistic and associated p-value. Similar to parametric tests, if the p-value is smaller than your chosen alpha level of significance, you will reject the null hypothesis and say that there is a difference between the distribution of the two groups. If the p-value is larger than the chosen alpha level of significance, you will accept the null hypothesis and say there is no difference between the distribution functions of the two groups. To report your analysis using this test, you would include the test statistic and the associated p-value. You should also include the median value for each group so that the reader will understand how the sample statistics are different. As a reminder, we report the median instead of the mean, since the median is a better measure of central tendency because the data are not normally distributed. You should also report the standardized effect size, R, as we discussed earlier in this lecture, to indicate the amount of clinical significance of your findings. The next non-parametric test that we are going to discuss is the Wilcoxon sign rank test, and this test is the non-parametric counterpart to the dependent sample t-test. This test should be run when you are comparing two measures for a group, but the assumption of normality from the dependent sample t-test has been violated. There are two assumptions for the Wilcoxon sign rank test that you must check before running the test. First, you should have a random sample, and second, the level of measurement for the dependent variable should be at least ordinal so that you can use ranking. For a Wilcoxon sign rank test, the null hypothesis would generally state something such as the median difference between the pairs of observations is equal to 0, and the alternate hypothesis would generally state something similar to the median difference between the pairs of observations is not equal to 0. As a reminder, this test is looking at the median difference between the change in the dependent group, not the medians of the group. So we talked about this with the dependent sample t-test, and it's the same concept. If we are doing a pre and a post test, we are looking at the change from pre to post. If we are doing a test where we are using two different types of measurement, say temperature that is an oral temperature versus a temporal temperature, we are looking at the difference in values from oral to temporal. Very important that you understand it is the difference that we are looking at. Again, you would use software to compute the test statistic and associated p-value. If the p-value is smaller than the chosen alpha level of significance, you reject the null hypothesis and say the median difference is not equal to 0. If the p-value is larger than the alpha level of significance, you accept the null hypothesis and say that the median difference is equal to 0. As a point of notation, if the median difference is equal to 0, that means there is no difference between the medians. I just wanted to make a note of that. To report statistical analysis using a Wilcoxon sign rank test, you would include the test statistic and associated p-value, as well as the median value for the group so that the reader will understand how the sample statistics are different. As a reminder, we're reporting medians instead of means for non-parametric tests, and you should also report the standardized effect size, R, so that your reader understands the significance of the effect and can identify clinical significance. The next two non-parametric tests that we are going to talk about do not have parametric counterparts that we discussed. This is not to say that they don't have parametric counterparts. They do. It's just that the parametric counterparts were not discussed in our course because they are rarely used in nursing literature and are beyond the scope of the course. However, often as a nurse researcher, you are going to be doing analysis where you are comparing more than two groups. And usually when this happens, your sample is going to be small and the data is going to be not normally distributed. If you are comparing more than two groups, so 3 or more groups, and the groups are all independent of each other, you will use the Kruskal Wallis test. An example of this may be if you are trying an intervention on 3 different nursing units and you want to assess the nurse's level of satisfaction on each of these units, and you want to be able to compare how the intervention was received on the 3 units. If we assume that the nurses only work on 1 unit, then you have 3 independent groups. Maybe you have your ER nurses, your ICU nurses, and your OR nurses. Each nurse is only in 1 group, but we want to compare the 3 groups, so we're going to use Kruskal Wallis test. There are 3 assumptions for the Kruskal Wallis test that you must check. First is that the sample is random. Second, that all 3 of the samples are independent of each other. And third, again, the level of measurement needs to be at least ordinal. For a Kruskal Wallis test, the null hypothesis would generally look like a statement that says the distribution functions are identical for the different groups. And an alternate hypothesis would generally be a statement that says something similar to the distribution functions are not identical for the different groups. Again, you would use statistical software to compute your p-value and your test statistic. If the p-value is smaller than the chosen alpha level of significance, you reject the null hypothesis and say that you reject the null hypothesis and say that the distribution functions are not identical. If the p-value is larger than our alpha level of significance, you accept the null hypothesis and say that the distribution functions are identical. It is important to note that the Kruskal Wallis test only tells us that the groups differ from each other. Once we identified that a difference was identified, as in our p-value was less than our alpha level of significance, we need to follow up by conducting Mann Whitney tests to compare every combination of 2 groups to further understand the variance. So we won't know the relationship between any individual 2 of our 3 or more groups until we also run the Mann Whitney test, which is the test for 2 independent groups, and we run that on each set of groups. So in my example of ER, ICU, and OR, we do a Mann Whitney for ER and ICU, a Mann Whitney for ER and OR, and a Mann Whitney for ICU and OR to get a more comprehensive amount of data. To report your analysis for the Kruskal Wallis test, you should include the test statistic and p-value from the Kruskal Wallis test output. You should also include the median value for each group so the reader will be able to understand how the sample statistics are different. And if your p-value was less than alpha and you rejected the null hypothesis, you should also report that a Mann Whitney test was used to follow up on the overall differences and include the results for all of your Mann Whitney tests using the reporting structure discussed previously. So you would say a Kruskal Wallis test was run to compare nurse satisfaction in the OR, ER, and ICU, and then you would further say if your p-value was less than alpha, that the that the Mann Whitney for the ER and OR was this, the ER and ICU was this, and the OR and ICU was that. This is further explained in our textbook with an example as well. The final nonparametric test to compare groups that we are going to discuss is Friedman's ANOVA. Sometimes investigators may be conducting more than 2 measurements on the same group. This could be when the same variable is measured at multiple intervals instead of just pre- and post-intervention, or when participants are exposed to more than 2 different treatments, such as comparing the temperature for an oral, temporal, and tympanic temperature. In these cases, you would use the Friedman's ANOVA test, and ANOVA stands for Analysis of Variance. There are 2 assumptions for the Friedman's ANOVA that you must check before running this test. First, the measures are independent of each other, and second, the level of measurement is at least ordinal. I want to clarify what I mean by the measures are independent of each other. What this means is that the measurements across groups or across patients are independent. Measurements for a single patient will not be independent of each other since they are measurements on the same patient, either over time or with different instruments. However, what this means is that if you are doing measurements at multiple points in time, each patient is only measured once at each time point. Or if you are doing measurements with multiple treatments, each patient is measured once per treatment. For a Friedman's ANOVA, the null hypothesis would generally look like a statement that says each ranking within the measurement is equally likely. And the alternate hypothesis would generally look like a statement that says at least one of the measurements produces different rankings than the other measurements. Again, you would use your software to compute the test statistic and associated p-value for the Friedman's ANOVA. If the p-value is smaller than your chosen alpha level of significance, we reject the hypothesis and we say that at least one of the measurements produce different rankings than the others. If the p-value is larger than your alpha, you accept the null hypothesis and say that each ranking measurement is equally likely. It is important to note that similar to the Kruskal Wallis test, Friedman's ANOVA only tells us that the measurements differ from each other. Once we identify that there is a difference based on our p-value smaller than alpha, we should follow up by conducting a Wilcoxon sign rank test to compare every combination of 2 measurements to further understand the variance. To report your analysis using Friedman's ANOVA, you would include the test statistic and the associated p-value. You should also include the median value for each repeated measurement so the reader will understand how the sample statistics are different. Also, again, if your p-value was less than alpha and you rejected the null hypothesis, you should report the Wilcoxon sign rank test used to analyze the overall difference and include those results as we discussed earlier in the lecture. To bring this lecture to a close and to summarize nonparametric tests for comparing groups, nonparametric tests are the counterparts of parametric tests. In this lecture, we focused on nonparametric tests that allow us to compare 2 or more groups when the assumption of normal distribution is violated. In general, most nonparametric tests analyze the rank of the data and not the actual data values, as we saw. The Mann Whitney test and Wilcoxon rank sum test are the same test in essence. They both compare independent groups and will produce identical test statistics. These tests are the nonparametric counterpart to the independent sample t-test. The Wilcoxon signed rank test compares 2 measures of a dependent group and is the nonparametric counterpart to the dependent sample t-test. The Kruskal Wallis test is a nonparametric test that allows us to compare 3 or more independent groups. And finally, the Friedman's ANOVA is a nonparametric test that allows us to compare differences when measures are repeated more than 2 times. All of the tests we discussed require our data to be at least at the ordinal level for ranking and so that we can compare the groups. In our next lecture, we will discuss some other non-parametric tests that can be used if we want to understand the relationship between 2 or more categorical variables, including addressing how to analyze variables at the nominal level of measurement, which cannot be ranked.